Hi guys, I'd just like to cover a few basics on the sequences and series section that you should know by the time you do your matric exams. So there are three basic sequences and series that we must look at. There's an arithmetic, a geometric, and a quadratic sequence and series. Now, the term sequence and term series it's effectively the same thing with one minor difference, and that minor difference we'll discuss later. But firstly, we need to look at number one, the arithmetic, or arithmetic, however you want to pronounce it, sequence or series. Okay, so we got that one. Now, what does that one mean? Well, it's fairly simple in the sense that it has a common first difference. And if we look at that more carefully, we can say, well, we have term 1, term 2, term 3, term 4. And we're saying that the difference between term 1 and term 2, which is simply done by saying term 2 minus term 1, is equal to the difference between term 3 and term 2, which we say is term 3 minus term 2. So we can formalize that and say, well, the common difference D is equal to term 2 minus term 1, and that's equal to term 3 minus term 2. Now, if we put this into a bit of a better example, we can say, well, let's make up a series. Let's say 2, 5, 8, 11. And we say the difference over here to here is 5 minus 2, which is 3, 8 minus 5, which is 3, 11 minus 8, which is 3. So we see the common difference D is equal to 3. And the formula for this is Tn being the term, that's term 1, term 2, term 3, Tn, general formula, is equal to A plus n minus 1 times D, where Tn is equal to the term, the actual term, so T1 is 2, T2 is 5, T3 is 8, T4 is 11. N is equal to the term number or term position, which means the position in which this term sits in the sequence. So for example, this number 5 is sitting at T2. It's sitting at the second position. The number 8 is sitting at the third position, and number 11 at the fourth position, etc. A is our first term, in this case 2, and D, as we've mentioned, is the common difference. Okay, so we have first term, common difference, term number, and the actual term. Now, if we try and take that sequence series and we make the general equation for that, right? The general formula, Tn is equal to A, which is 2, plus n minus 1 times D, which is difference of 3. We can simplify that, I suppose, and we can say, well, 2 plus 3 times n is 3n minus 3, and we end up with 3n minus 1. So Tn is equal to 3n minus 1, and that's our general formula. Okay, so arithmetic sequence is as basic as they come. I don't think you'll get much of that, but we've done it anyway. The next one, number 2, is a geometric sequence. And how does a geometric sequence differ from an arithmetic sequence? Well, the difference is the one had a common difference, and the geometric sequence has a common ratio. And what if we look at this, we're simply going, well, term 2 divided by term 1 must equal term 3 divided by term 2. That goes for the same term 1, term 2, term 3, and term 4. The ratio between term 1, thing's messing up on me. The ratio between term 1 and term 2 and term 3 and term 4 must be the same. So that's defined by this formula over here, and that's the general formula for R. So we can say R, being the ratio, R is equal to that. Now, we also have a general formula. The general formula is just as easy as the previous one, where Tn is equal to A times R to the power of n minus 1. Now that A, once again, A is equal to the first term. R is equal to the common ratio. N equals to the term number or term position as in the previous one, and then Tn as a thing is equal to the actual term value. So 5, 8, 10, whatever it is. Okay, so if we have a look at a quick example for geometric, we can say, let's say we've got 5, 10, 15, maybe not 15, 5, 10, 20, 40, right? We say, okay, term 2, which is 10, divided by term 1, which is 5, must equal term 3, which is, term 3, which is 20, divided by term 2, which is 10, and we see the common ratio here is 2. That means that Tn is equal to A, which is 5, R, which is 2, to the power of n minus 1. And it's important to note that this guy here, this piece here, is separate from this 5. So when we work it out, it's the same as saying 5 times 2 to the power of n minus 1, whatever that is. So the 5 does not get that power. So sometimes people make that mistake. It is separate. So when we look at that, often they simplify it, and they simplify it by saying, well, this is simply the same as saying 5 times 2 to the power of n times 2 to the power of minus 1. Right? We can simplify this exponential or exponent by doing that, and then it's the same as saying, well, 5 divided by 2, because 2 to the minus 1 is the same as saying 1 over 2. So 5 times a half is 5 over 2, times by 2 to the power of n. So sometimes people like to simplify it like that. I don't bother. I leave it in this form, but it's up to you. Okay, so the third and final sequence that we look at is called a quadratic sequence. And this differs from the other two because it has a common second difference. So unlike the arithmetic one, which had the first difference was common amongst all the terms, this one has a common second difference. So rather than explain it using letters, as I did the previous two, because it gets a bit more complicated, we just explain it with an example because it's easier to follow. So let's just write an example. So we have 2, 5, 10, 17. And that's our sequence, and we say, well, the first difference between these, clearly it's got no common ratio. The first difference between these two is 3. The next difference is 5. The next difference is 7. And the common difference between 3 and 5 is 2. And the difference between 5 and 7 is 2. So we see we've got a second difference. So this guy here is the first difference. And this one over here is the second. Second difference. Now how do we actually solve this? Well, firstly we've got to define what the equation is. And the equation for this is Tn is equal to an squared plus bn plus c. Now we've got to figure out what this a value is, what this b value is, and what that c value is. So how do we do that? Well, now this is where we have to remember something, unfortunately. We say 2a equals, and we write it like that, We go then 3a plus b equals that one, and a plus b plus c equals that one. Now that's not very difficult to remember. There are other ways to do it, but I don't recommend them. And we solve from the bottom up. So we solve. Okay, my pen's not working again. Great. And we solve from the bottom up. So let's just solve these. So the first one we saw was 2a equals 2, therefore a equals 1. The second one, we see that 3a plus b equals 3. We know what a is, 3 times 1 plus b equals 3, so b must equal 0. And then we can solve for the third one, which was a plus b plus c equals 2. So we say, well, a plus b plus c equals 2. And we know what a is 1. We know what b is 0. So we can calculate c. So c must equal 1. 2 minus 1 is 1. So we get, now we've now got our a, we've got our b, and we've got our c values. So therefore, Tn is equal to an squared, a is 1, so it's just n squared, plus bn, which is 0, plus c, which is 1. So Tn equals n squared plus 1. And if we look at the original sequence, we just double check, always double check. Let's plug in a value, and we say, what about T3 to calculate the third term? Never calculate the first term, because that it's not going to show you if it's right or not, but we're expecting to get 10, right? The T3 is 10, so we're expecting to get 10. So T3 is 3 squared plus 1, which is equal to 10, which is what we were expecting, so our formula is correct. Everybody's happy. Okay. The next thing I'd like to look at is just a series. So how does a series differ from a sequence? Well, it's actually the same thing. The only difference is a series is the addition of each term in a sequence. So let's take an arithmetic sequence. Right? As I showed before, an arithmetic sequence, in fact, I'm going to use exactly the same one, just so we all on the same page. And in this case, I use 2, 5, 8, 11. So let's just use the same one. 2, 5, 8, 11. And we can convert that into an arithmetic series by simply adding them together. So we have 2 plus 5 plus 8 plus 11. Everything else remains the same. The same formula, so Tn is equal to a, which is 2, plus n minus 1 times d, which is 3. It's exactly the same formula. And the same formula over here. Tn is equal to 2 plus n minus 1 times d, which is 3. So why do we define them differently? Well, because this one we're summing. So if we say the sum of the first 5 terms, we can actually get a sum. Now we can sum these ones as well. It makes no difference. Like I say, the only difference is the name, and the one's got commas and the other one's got a plus. everything else remains the same. Same formula, same everything. So what is the sum formula? The sum formula, Sn, and that says the sum of n terms. If n is 10, it's the sum of the first 10 terms. Sn is equal to n over 2 times 2a plus n minus 1 times d. So we have our Sn formula, and that says that the sum of some n terms, however many n terms, whichever n terms they are, is equal to this little formula over here. A is the first term, d is the difference, and n is the term number. It's exactly the same as before. This can also be written a little bit differently, which is everybody's favorite, sigma notation. It's a horrible sigma. Let me just rewrite that. Okay, so sigma notation. Now, sigma notation is just the same as saying little n from 1 to big N of Tn. Right, so we've now got sigma notation. I'm sure you guys love sigma notation. And all that says is it's this sum formula, Sn, written in a different way. So what sigma notation says, that sigma notation is the same as Sn, which is equal to the above equation, n over 2, 2a plus n minus 1 times d. Now, why use sigma notation? Well, sigma notation is a shorthand version of writing that, and you can do cool things with sigma notation, but mostly to confuse you guys. So if we look at sigma notation, just to note, it's literally the sum of each term. That is what sigma notation says. So it says the sum from n equals 1, in other words, term 1, to some random n, the 10th term, the 20th term, the 30th term. Okay, so that's all it says. And this Tn is the formula. So if we want to expand that, we can expand it by saying, well, it's the sum from little n equals 1 to big N of Tn. But what is Tn? Tn is a plus n minus 1 times d. So we can write it as a plus n minus 1 times d. That is equal to Sn, that sum formula over there. Okay, now we got that out of the way, we can just discuss one of the properties of this. This will never converge. The sum to infinity of an arithmetic sequence cannot converge. It will always diverge, and what that means is it will always get bigger and bigger and bigger. If we look at a graph of two things that are converging, let's say starting at some point, and it goes like that, and something else does that, and it goes like that. They are converging. These two lines, line A and line B, are converging. They're coming together. And it doesn't have to do that. I mean, you could have any two lines. You could say something like this. It's converging. This thing is converging. It's starting at some weird thing. It's doing something, but then it converges. It goes to a point. What is that point? Well, we can calculate that, but that is a convergence. It is coming to a value, a number, something like that. That's converging. If we look at diverging, diverging is when two things go away from each other. That is diverging from this point. So this one, this first one here, converges to a point, whereas this one over here diverges from a point. So an arithmetic sequence or series will always diverge as it tends to infinity. Okay. If we look at a geometric, so geometric series, once again, it's the same as a geometric sequence. So we have Tn is equal to AR n minus 1. Exactly the same as before, but the sum formula is obviously slightly different. Sn is equal to A 1 minus r to the power of n divided by 1 minus r, and you could write it, I suppose, Sn is equal to A r to the power of n minus 1 over r minus 1. Now it doesn't make any difference. What people like to do is they like to use this one when r is bigger than 1 and use this one when r is less than 1. But doesn't matter. Well, not less than 1, but is a fraction. So in this case I'm assuming it's positive, but you could say r is a fraction, so less than 1 but bigger than negative 1. And here is r is bigger than 1 but smaller than negative 1. Anyways, the point is there is no difference between these two formulas. If you plug in something where r is a fraction, you're going to get the same answer regardless of which formula you use. So I'm only going to use the top one, the first formula. Why am I going to use that one? Well, because this is the one that's used when we do sum to infinity, and I'll explain that now. So previously we said the arithmetic series never converges, it always diverges. Well, geometric's a little bit different. If we take this sum to infinity, right, and we say, okay, whatever our a value is, it's our first term, 1 minus r to the power of n, which is infinity, divided by 1 minus r. If r is a whole number, a big number, let's say r is equal to 2. 2 to the power of infinity, right? So 2 to the power of infinity is some infinite number. It's really big. So what we have here is we have a times some really, really big number divided by 1 over 2, or divided by 1. And we get some really big numbers, so it just diverges. So what we end up with is this thing just shooting off to infinity. It diverges. But what happens if r is not a whole number? If it's a fraction? So let's say r is equal to 1 over 2. What is 1 over 2 to the power of infinity? Well, if we take our calculator and we say 1 over 2 to the power of 10, we're going to get a fairly small number. If we say to the power of 100, that number is going to get smaller. But your calculator cannot tell you how small that number is, so your calculator will actually tell you 0. So if you put a half to the power of not quite 100, because your calculator will run out of memory, but if you put 99, for example, then or 98 or whatever your calculator can take, your calculator will give you an answer of 0. And why is that? Well, a half times a half is a quarter. A quarter times a half is an eighth. An eighth times a half is a 16th. So you can see it's getting smaller every single time, and you're doing it so many times that you tend towards 0. You're taking the limit of that as it tends to 0. So what you end up with now is you end up with something that converges. Converges because you're adding or you're subtracting 0. So you're going to end up with something that converges to a point. In this case I've drawn it converging to 0, but it doesn't. That represents this. So that sum to infinity, if r is a fraction, plus between, let's write some space, I'm going to change color quickly. If r is less than 1 but greater than negative 1, in other words it's a fraction, a positive or negative fraction, we end up with sum to infinity equals a 1 minus 0, as I showed over here, divided by 1 minus r. And that one can be simplified to a over 1 minus r. And now we have our sum to infinity formula. Right, so that's our sum to infinity formula. And that's why I prefer using this number 1 over here. Okay, so a geometric sequence or series will converge if r is a fraction, or more technically correct, if so convergence condition, and this only happens with the geometric, is r must be bigger than -1 but less than 1, and that is very, very important. Okay, and that'll give us our sum to infinity. So this is the condition that you need for sum to infinity. Okay, and that's it. Once again, you could say, well, if you use sigma notation, n equals 1 to n of Tn. Obviously Tn is slightly different, so it's the sum of n equals 1 to n of Tn, which is ARn minus 1. But otherwise everything else remains the same, and that's still equal to Sn, still equal to Sn. Okay. And then you generally don't sum quadratics. So, well, you can, but in this case, in your maths, you don't sum your quadratics.